Hi all, in today's class we are going to start with chapter 12, which is Boolean algebra. And I just touched upon this chapter when we were discussing about truth tables and how we can use logic gates and something similar we can get. So in this chapter we are going to learn about Boolean functions, then how we can represent Boolean functions, and then logic gates. Now this is the last chapter which will be there on your final exam. So till chapter 12 we are going to cover part of your final exam. Now I am also planning to cover some important topics from chapter 13, but for that we will do a discussion board assignment, and that part will not be there in your final exam. So till chapter 12 we will have everything covered on your final exam. So in this case, since this chapter representation is very similar to chapter 1, we are going to go through similar concepts, but now we are going to represent those concepts in terms of ones and zeros, like how we want to do it or how we want to build it in terms of logic gates, and then how internally in our computer everything is represented again in terms of bits. So here we need to learn how these Boolean functions are represented, and as a section summary we can say that we are going to have some introduction of how Boolean algebra works and how Boolean expressions are written. And then if you remember the laws of De Morgan laws and the identity laws, so some similar laws are applicable in Boolean algebra as well, and you can very much easily draw the parallels between our chapter 1 and chapter 12, because there are a lot of similarities, only the way of representation is different, and every notation that we saw, like A and B or C, all those notation we can represent using logic gates. So that is one more important thing that we are going to learn. So if you remember, we saw there are 3 logic gates, but again we want to see that again, and any given notation or equation we can represent using the logic gates. So how we can do that part also we are going to learn. So here if we saw, now it is showing me what I did last time. So let me grab eraser. Okay, unless I write, I think I don't get eraser. Okay, now I get it. Okay, so what I will do is I will draw some tables, and I will draw the parallels between the truth table and this. So when we saw in truth table, we have equations such as P and Q, and when we have to consider this combination, we have to consider 4 different possibilities of values between PQ, and then so sometimes P can be true and Q both are true. Sometimes P is true and Q is false. Then it might be the case that P is false and Q is true, or it might be the case that both are false. So here we whenever there are two variables, we have 4 different possibilities that we need to consider. And when we are talking about P and Q, then we know that P and Q is only true when both of them are true. And so only for the first case it is going to be true. For all the remaining cases, P and Q gives us the value as false. So this was the truth table for P and Q. Now something similar happens in the Boolean algebra, but in case of AND, now we show AND function as a dot. So when we say P and Q, and instead of now here true, we use 1, and the false is replaced by 0, which is the value of that particular bit or bit value. So when we have to build truth table for P and Q, it will look something similar, but only instead of true it's going to get replaced with 1, and wherever it is false, it's going to get replaced with 0. So now my truth table becomes, again, since there are two variables, we have 4 possibilities. So either both are true, which is shown by 1 1, or one is true, one is false, and then the one is or P is false, which is shown as 0, and Q is true, or both are false, which is shown as 0. So 0 meaning false and 1 meaning true. And then here this AND function will only be true whenever both are true. So that will be 1 only for the first term. For all the remaining terms, it is going to have value 0. And this is 1. Now, if you remember the OR function or disjunction, in that case we show that P or Q, and P or Q is true when both or either P or Q is true. So if whenever any one of them is true, we are going to have the value of P or Q is true. So in the original truth table, if we have both true, then P or Q is going to be true. If we have P true and Q false, then P or Q is true. If we have P as false and Q as true, still we have it as true. And when we have both false, in that case we have the value of P or Q as false. Now here, very similar strategy we have, but the OR symbol is shown by plus sign. So we have P or Q is shown by P plus Q. And again, instead of true, we are going to use ones, and whenever instead of false, we are going to use 0. So I hope the eraser works now. Okay. P, Q, and then the truth table will be exactly same. So replace true by 1. So 1 is one possibility, and in that case it is 1. Then 1 0 is another possibility, in that case it is 1. Then 0 1 is another possibility, in that case it is 1. And then last possibility is 0 0, and in that case it is 0. So the exact same parallel we can draw between the propositional logic and then Boolean algebra, but in this case these are treated as bits, and then instead of true false we are using 1 0 to represent the truth tables. And similar truth tables, if we have 3 variables and then we have to draw truth table for Boolean algebra, it will be something very similar that we did for our propositional calculus. Now it has its rules which we saw, which are very similar to our propositional logic, and then but every time every element is drawn from set 0 1, and every equation will also have value either 1 or 0. And then we have 3 basic operations here, something similar to the propositional logic. So plus is called as sum, or this is equivalent to our OR operation. And then Boolean product operation, which is equivalent to our AND operation. And then complement operation is similar to the negation operation that we did. So whenever we say complement of 0, we get 1, and then and we get complement of 1, we get 0. So it's basically negation of any given number. So if we have Boolean sum, you can see that Boolean sum is nothing but it is something similar to OR that we just saw. So if you do 1 plus 1, you get 1. If you do 1 plus 0, you get 1. If you do 0 plus 1, you get 1. And if both P and Q values are 0, then only you get the sum as 0, as shown in this particular truth table. Now how about product? Product is similar to and we can see that only when both values are 1 we are going to get product as 1. If either values is 0, then if one value is 1 and another is 0 we get 0. If one first value is 0 another is 1 we get 0. If both are 0 we get 0. And complement, 0 complement is 1, 1 complement is 0. So using this can we find value of a given equation. Now this 0 plus 1, it means nothing but it is similar to our OR function. So if we do 0 plus 1 here, that gives us, or that is a Boolean summation, it gives us value 1. So this particular equation, it gives me the value 1, and then I have complement of 1. So this particular part gives me value 0. Okay, how about this part? 1 product 0. Now product, for a product to be 1 we need both values to be 1. Here one value is 1 and another is 0, so the product we get is 0, and finally it is 0 sum 0, which gives us 0. So using this, if we have any expression given, we should be able to evaluate that using these three basic operations. And as we know that sum work exactly similar to our OR function, and product works exactly similar to our AND function that we did in propositional calculus, and complement works exactly like the negation that we did. So there might be any function that we can create using two values. So how many functions we can create for a given xy values? So here let's say we have b as 0 1 is set of two values, and then bn is the number of functions that we can generate from these two values. So how many functions which we can generate? So if we have two values for a given function, we know that there are 4 different possibilities, and then those 4 different possibilities we can show differently for those. But how many such functions we can build from the 4 different possibilities they are asking? So here is one example function fxy where we have two values of xy, and this function actually works something similar to the XOR function. Actually not really XOR. This function is a different function where when both the values are same, then it is 1. So when x and y both are 1, then it is 1. If x and y both are 0, it is 1. So they have not told us which function it is, but let's say there is one function on xy, and it acts in such a way that when both the values of x and y are same, then the function is 1, otherwise the function is 0. So we can say that in this scenario, this particular function we can build, and now we have to say that a function from bn to b is called a Boolean function of degree n. And then we have to see how many variables are there. So here we have 2 variables, so this is a function of degree 2. So this is called as function of degree 2 because we have 2 variables xy. Now they want to know how many such functions we can create using 2 variables, and what do you think, how many functions we can generate like that? So when there are 2 variables, there are 4 possibilities of this. So it might be 1 1, it might be 1 0, it might be 0 1, and it might be 0 0. So these are 4 possibilities. So the total number of functions that we can generate will be 2 raised to 4 because there are 4 different possibilities, and so we can generate 16 such functions. So each time we can have, because there are 4 different values, and we know that 4 bits can have 2 raised to 4 different combinations. So we can have all values of x, y, 0 0 0 0. Then we can have So these 4 values we can have one function giving all zeros, one function giving 0 0 0 1. Okay, another function will give us, let's say, 0 0 1 0, and so on till we have all the function giving us all values as 1. So if you calculate how many such possibilities are there, then from 0 to 15 we have 16 such possible functions which we can build from just two values of xy, or degree 2. We can generate 16 such functions. Now we don't know what each function is called. So out of this, one might be the sum function, which is similar to OR. One might be the product function, which is similar to and then there are 14 other functions that we can generate from just two variables or having degree 2. So they have given a nice table for this. In coming slides we will see. So when we have to find the values of some Boolean function now, which is given to us xy plus z complement. So how we want to generate this function? Again, we will do something very similar what we do in propositional logic. What we will do is we will consider x, y, z, and since there are 3 different variables, we have 2 raised to 3 which is equal to again 8 different possibilities we have. So we start from 4 here, 4 1 4 0, then 2 1 2 0 2 1 2 0, then 1 0 1 0 1 0 1 0, and we get these 8 different possibilities. Now the first thing we need to do is the product of x y, which is similar to AND. So whenever x and y both are 1, then my xy is going to be 1. So here my xy both are 1, this is 1. Again in second row, xy both are 1, so second row is 1. In the all remaining rows, either x or y is 0, so you can say that all the other rows are 0. Okay, now z, we have different possibilities are z, and we are calculating the z complement. So whenever z is 1, z complement is 0, and so on, and then this column is calculated. Now our function says we have to do a sum of xy and z complement. So when we have to do summation, which is similar to OR function. So if either of these is 1, then the value we get is 1. So for the first row 1 0, so we get 1. Second row 1 1, so we get 1. Third row both are 0, so we get 0. Fourth row 0 1, we get 1. Fifth row both are 0, so we get 0. In sixth row z complement is 1, so we get 1. Seventh row both are 0, so we get 0. And eighth row z complement is 1 and we get 1. So we see that we can calculate any given function by creating a truth table or something similar what we did, but we have to make sure that how we are implementing this Boolean functions instead of the previous propositional logic. So this is something similar, and I expect that you should be able to generate truth table for any of the given expression, and this expression is called as Boolean function. Now this, because this is something given as a function and it looks like algebra, so this what we do with this is also called as Boolean algebra. So we have to make sure that how many variables are there, 2 raised to those many, and then those many values will be there in our truth table. Now next, the definition is that Boolean functions f and g of n variables are equal if and only if whatever f we have and g we have, and then b1 b2 up to bn belong to some b, and two Boolean expression can represent same function when they are equivalent. So the complement of Boolean function f is the function f bar, where if you complement whatever you get from applying that Boolean function, or you complement the whole function, you should be getting same value. Another definition is if f and g are two Boolean functions of degree n, and then you want to do the or Boolean sum of f and g and then Boolean product of f and g, then you can do something like this, that you apply the Boolean function f on your set and then you apply g on your set and then you add, and when you have to have product, then you apply f first on the variables and then you apply g on the variables and then perform the product of both. Here is a nice table which shows us whenever we have degree 2, meaning we have two variables, how many different functions we can have. So if we have degree 1, it means that we just have one variable x, okay, and the x can take value 1 or 0. So we have these two values can be taken by x, and then we have some function f on x, and how many typical functions we can build on x. So we can say that for value of x, so there are two possibilities, so two values of x, so there are 2 raised to 2 possible functions. So one function might give me 0 0, another function might give me 0 1. Okay, so let's call this as function 1. Another function might give me 1 0, so let's call this as function 2. And then another function 3 might give me both values as 1, and those are the only functions that I can build when I have a single variable. So whenever I have degree 1, I have two possible values of that one bit or one variable, which is 1 or 0, and for each of these two values I can build 4 functions. So one function might, so let's call this as function 0. One function might give me value 0 0, another function might give me value 0 1, one function might give me value 1 0, and another last function might give me value 1 1. So that's all. There will be only 4 such combination. I cannot have more than that because since there are only 2 values that x can take. Similarly, if when we have degree 2, it means I have 2 variables. So they have given here the example, so x y. Now x can take these values, so both together they can have 4 different values, so 1 1 1 0 0 1 0 0, and then we can build for these 4 different values, we can build 2 raised to 4 different functions, so which gives us value 16, and that's what this table is saying. So when we have degree 2, we have 2 raised to 2 rows, and for each of these so we have basically 4 possibilities, and each of these 4 possibilities we can generate one function, so we can actually generate 2 raised to 4 such functions, which is nothing but 16, which is given here. So what are the 16 different functions can be generated? So one, again, different 4 bits taking different values, so starting from 1111, 1110, 1101, and so on up to 0000. So these are 16 possible functions that we can build when we have degree 2. So we can say that when our degree goes to 3, we have 2 raised to 3, 8 rows, and then we can generate 2 raised to 8 functions, which is given by 256 and so on. So when we have 4 degree 4 variables, we can generate 16 rows, and then the number of functions we can generate is 2 raised to 16, which is given by this 65,000, this number, and so on. So you can say that see that at only around degree 6, so if we have 6 variables, we can generate almost huge number of functions out of those 6 degrees. Then here are some identities of Boolean algebra, very similar to what we saw. And you can see that whenever there is a double complement, so you complement x once and then you complement it again, then you get your original x. So if you have 0, if you complement it, you get 1. You complement it again, you get 0 back. Then the idempotent laws, so product of x with itself is whatever the value of x. So if you have x as 0, you multiply it with 0, you get 0. If you have x as 1, you multiply 1 with 1, you get 1. Or you get product of 1 multiply 1 by 1, you get 1. And then x sum x, so if you have 1, you sum with 1, you get 1. If you have 0, you sum with 0, you get 0. So whatever is the original value of x, it preserves. Then identity law, whenever we are having or sum with 0, we get the original value, whatever value of x is. And then whenever we are doing product with a 1, then we are getting again whatever value x has. Then whenever we are having sum with 1, irrespective of what value x has, we will always get 1. So that's why it is called as domination law. And then whenever we have 0, if we are having product with x, we will get 0. Then cumulative laws, whether you do the sum or product in one direction or another direction, you get the same result. So whether you add 1 to 0 or 0 to 1, or whether you have sum 1 sum 0 or 0 sum 1, it is one and the same thing. Again, similar to product, Boolean product, if you have xy product or yx product, both will give you same results. Again, these notations are associative. So if you have something like this, x plus y and plus z, so we can see that actually this should not be there, this y should not be there. Okay, so if you add or if you have Boolean sum of xy first and then you have Boolean sum with x, or you first have Boolean sum of yz and then you add x, both will give you same result. Similarly for the product as well. The distributive laws, again, if you have something like in the inside bracket, then it gets distributed, something similar to what we do in case of our Boolean or algebraic equations. So if you have x outside and then product with y plus z, then actually you can also write it as x product with y plus x product with z. Then De Morgan's law. So these are exactly similar to our and or laws. So if you have negation of or complement of Boolean product, you get x complement and sum y complement. And then if you have complement of the Boolean sum, then you get x complement product y complement. And then absorption laws, so when we have x plus xy, then whatever value of x you preserve. Then unit property, meaning that if you add x and x complement, it will always be 1, and if you have Boolean product of x and x complement, it is always going to be 0. So using this law, actually we can show some identities, or we can also show if given two equations give us same value or not. So that is also possible by solving this kind of equations. And if we want to show that a distributive law that we just discussed, that if we have x product with y summation z, then can we have xy plus a or xy sum xz, and then we can show that using truth table. So since there are 3 different variables, we have 2 raised to 3, 8 different values in this truth table. And we can see that first what we will do is we will just calculate the y sum z, and so it is 1 because yz is 1, y is 1, z is 1. Then in fourth row both are 0, so it is 0. In fifth row both are 1, in sixth and seventh row either one of them is 1, and then in eighth row both are 0, so you can see this yz. And then we want to multiply, or we want to have product with x, and if we have product we can see that first 3 rows will be 1 and the remaining all rows will be 0 because all other rows have something, at least one of them is 0. So we saw here that x, so x multiply or x product y sum z has first 3 rows as 1. And now individually we want to try if we do the sum of xy and xz, are we getting the same truth table. So if we do xy, we can see that first 2 rows are 1 1 and then remaining are 0. If we do xz, we see that first and third row is 1 because values of xz are 1 and all the remaining are 0. And then when we add or when we do the sum, we see that first 3 rows are 1 here as well. So we can see that it can be proved that the distributive law is indeed applicable in case of Boolean algebra. Now these are some identity laws, and then those are in this case they have shown it using this binary operation or and along with the elements 0 and 1. So the set of propositional variables with the operators and or and elements true, false and negation operator is also part of Boolean algebra. So sometimes we can interchangeably use these two binary operations on the elements 0 1 as well. So if we say x or 0, we get x. If we say x and 1, we get x. If we say x or x complement, we get 1, x and x complement 0, and then some similar laws. I will not explain everything, but the laws are similar to what we saw, but we are using it in case of Boolean algebra. And here the only difference will be the resulting values will be zeros or ones instead of true false that we saw earlier. Now here is one how we can represent different functions, and then whether using truth table or otherwise. So if we want to represent f, here we need one term x y complement z because it has value 1 when x and z is 1 and y is equal to 0. So if we have a given function given as x, y complement and z, then we know exactly that since it is a product, so even if they haven't shown the dot here, actually sometimes we can use dot, sometimes if we don't want to use, that is also fine. So in this case we can see that the value of this is going to be 1 only when x is going to be 1, z is going to be 1 and y complement is going to be 1, and that will be only possible when y is equal to 0, and in that case our y complement will be 1. So here we can see that is the only case when it is going to be 1. So this is the case when it is 1. Now to represent the function g, now what is the function g? We use the sum, and now this is x y z complement and x complement y z complement. Now we have to check when this expression will be 1, and looks like this expression is 1 for this particular scenario when x is equal to 1, y is equal to 1 and z is equal to 0, or it is also true when x is equal to 0, y is equal to 1 and z is equal to 0. So in this case also it is giving us one value. So for each combination, we have to find the values of variables for which the function has value 1 in terms of Boolean sum, that is the Boolean product of the variables or complement. So we need to find out such values when this function value becomes 1, and that's how we can solve any given function or find the values of xyz when this particular function will be true. And we can either now here it is pretty straightforward, but just looking at this combination we can say that what should be the values of x, y and z in the first case. In second case it is not that straightforward, but you can see that since there is a summation here, there are two possibilities, so two sets for which the value will be true, either when x, y both are 1 and z is 0, or when x, z are zeros and y is 1. So that's how we can have that intuition for which values in my truth table I'm going to get the value as 1 for this particular expression. Now a literal is a Boolean variable or its complement, and a minterm of the Boolean variables x1, x2, xn is a product, Boolean product y1, y2, yn. So if these are different terms how we can really represent the products in case of Boolean algebra. So minterm is a product of n literals. So we call this particular variable as a minterm when it is shown as a product, and in that case if it is product then it is easy for us to find the truth values, because we know that only it will be true only when all the variables are going to be true. Now a minterm y1, y2, yn has value 1 if and only if each of this term yi is 1, and this occurs only and only if xi is 1 when yi is equal to xi and xi is equal to 0 when yi is equal to x complement. So if there is another complementary term, then we can have that discussion. Like in the previous case, here we needed y complement to be 1, it means y needed to be 0. So in case of summation, in case of products it is straightforward, but as I said, in case of sum, we generally are looking at two possible values when it is true. So in this case, either whenever x is true or y is true, this is going to be this part is going to be true, and then whenever z complement is true or z complement is 1, then for this function we get value 1. So here we use two methods. First we just going to draw the table, and then we want to find where I'm getting value 1. So for that I can first generate x sum y, and I see that there are for first 6 values I get value as 1. Then z complement, again whatever value of z I'm going to complement that, and this is the truth table. And when we do the product, we see that we get value 1 at second row, at fourth row and at sixth row. So these are the values, and then from the truth table we can say that when x is equal to 1, y is equal to 1, z is equal to 0. So we can also come up with the possible values of x, y, z that will satisfy this given equation. So x is equal to 1, y is equal to 1 and z is equal to 0. So this is one possible combination, and we have 3 such combinations. So second combination is when x is equal to 1 but y is equal to 0 and z is equal to 0, and another combination is when x is 0, y is 1 and z is 0. So those are 3 possibilities. Now this is one way. What is the second way of finding the sum of minterms corresponding to each row? And when we include each term for each row of the table, then we can see that So those terms, those possible terms, or if we want to solve this equation, it is possible that we can show that. So these values we can show actually when x is equal to 1, y is equal to 1, z is equal to 0, that can be shown as x multiplied by y, x, y, z complement. The second set value, as I said, was x is equal to 0, x is 1, y, z are 0, 0. So which is shown as x, y complement, z complement. And then the third row, which is x and z are 0 but y is 1, that is shown as x complement, y, z complement. So this is another way of showing that these three different values are satisfying this equation, and this is nothing but the product of this, or we can say sum of products. So this is also called as the sum of products method, because we are finding the number of ones and then we are expressing those different values of x, y, z as sum of the individual products. So we found the three rows, and then those three rows we took for which values they are satisfying. So if it is satisfying for value 1, we are writing it as it is xy. If it is satisfying for value 0, we are taking complement, and then we are saying these are the three values for which this given expression is satisfiable. So this method is called as sum of products expansion. And then we want to find if it is indeed possible to expand this given equation into this form by using some now the rules that we already saw. So this was the truth table method, but can we expand it using the rules or the laws that we already saw? So here if we first use the distributive law, we can expand it as xz complement plus sum yz complement, and then now we have to add another 1 here as a product, and then we can see that x and 1 we can show as y sum y complement, and here this 1 we can expand as x sum x complement. And we wanted, because both these equations are really equivalent, but we just wanted to make sure that these are equivalent using the Boolean identities. And then when we expand this, we saw that this is what we get, and then using the idempotent laws we can get rid of one of the terms because this term is same. So xyz complement we are getting twice, so we will merge it as 1 and then the remaining 2 terms, and that is exactly what we got from the truth table. Now again you can use truth table, you don't have to use the expansion rules, because you can see that the expansion rules are not very intuitive, because every time you have to come up with the new rules. So as long as you understand how from the truth table we are getting this, you are good. Then so every Boolean function can be represented using these different Boolean operators that we saw. So we can either use the product operator or sum or complement. So we say that this set is functionally complete set, because every operation that we can show as using this basic operation. So something similar to the primary colors. So we know that every color we can generate from primary color, and those are complete. So similarly these operators are complete in themselves, because any operation we can show using combination of these operators. Now the set, again product and complement, it is also functionally complete because we can show the sum in terms of complement of the product. So we can also do that, and then if we take the double complement, that will also give us something similar of this sort. So it is also possible. So this is not actually, this is merged, but I will draw it here. So it is nothing but x complement product y complement and product of that. So if we what happens here is, if we use the De Morgan's law, then this complement will change, and this will be equivalent of saying x complement sum y complement, and that is nothing but x plus y, or x sum y. So again, using this two, we can, using only these two operators, we can show any Boolean function. And similarly, using these two also, they are functionally complete, the sum and complement, because we can also show the product by x complement sum y complement. Again, similar to this, applying De Morgan's law, we will reach to this conclusion. So there is another operator, NAND, or negative AND operator, and it is denoted as straight line. And then what it does is, it does exactly opposite of the AND operator. So we know that AND operator does 1 when both are 1. So when both variables are 1, we get 1. And here, when both variables are 1, we get 0. Then when either of them is 0, we get 0 in our AND operation. But here, when any one of them is 0, we get 1. So this set is again just one operator. It is functionally complete, and we can see that every other operations that we just saw, all other operations that we just saw can be represented using just this single operator, which is negative and then here we can show that x complement can be shown as x and this negative and xy can be shown as x negative and y negative and x negative and y. So if we solve this, we are getting something similar to this, and then we can see using truth tables that it indeed is a complete operator, and it is very important operator for the same result, because almost every Boolean equation, function, algebra, you can show just by using this negative AND operator. Then NOR operator, again it is negative OR operator, and you can see the notation is downwards arrow. Now it takes the OR function and it negates the OR function. So in OR function, whenever you have both 0, you have it 0, but in this case, whenever you have both zeros, you have it as 1, and whenever anything is 1, you are going to have the combination of it as 0. Again, the set consisting of only one operator, and if we use only this NOR operator, we can generate a functionally complete set. So now we are going to go forward and have a look at the logic gates and how we want to represent different Boolean expressions using logic gates. So there are three main logic gates, and one is inverter. So inverter does nothing but take input and does the complement of that input. So if you give 0, it gives you 1. If you give 1, it gives you 0. So just does the negation of given value of x. And then the second gate is called as OR gate. What it does, it does sum of two variables. So if you insert two variables xy, then it gives you summation of x and y. So x sum y, and the truth table is something similar to OR when the first truth table that we saw. And this is the AND gate. So this is OR gate, so the truth table is similar to the OR, and this is AND gate, the truth table is similar to the propositional logic of AND. So whenever you have both x, y 1, then this x, y will be 1, and so on. So basically, since they are using the same names OR and AND, like propositional logic, you can see that the output is also same as OR and AND gate, but just the representation is different. Here you are not saying x or y, here you are saying x sum y. You are not saying x and y, you are saying x product y. And then inverter you are saying complement. Then this is the negative and I think this this is the and OR gates with multiple inputs. So if you have from x1 to xn and then multiple inputs, and then if you do the AND of multiple inputs, you get x1 product, x2 product, x up to xn. Then for OR gate, if you do it for n variables, you get x1 sum x2 sum x3 and so on, or x1 x or x2 x3. Now whenever we have different Boolean expressions, we need to use the combination of the gates to show the expression. So here is one way, or here are two different ways of constructing a circuit that produces xy sum x complement y. So how can we generate this? Now this is xy is a AND gate. We can see that this is a product. So the first thing they did is given x and y input to the AND gate, and we got the product, which is xy. Now in the second part, we need the complement of x, and then we want to add it with y. So here inverter is used to get complement of x, which is x complement, and then that and y is given to the AND gate to get this complement, to get this AND operation. So x complement y, and now this both have to have summation, or so for that we need OR gate. So we give this to OR gate, and in the end we get this expression. What is another way of doing the same thing is that instead of having xy taken differently, here xy and again here xy, we can get rid of this xy and we can pick xy from here itself. So you get, first you do give xy to AND gate, and then you get the product of xy. Then you pick y as it is, and for x, and whenever there is a crossing, the line is shown as curved. So that is a general notation thing that we need to follow. So whenever we cross one line, we just need to show it as a curved line. Then we need to invert this x to make it as a x complement, and then we give x complement and y, and then get x complement y, and this 2 we need to give to OR gate to get the sum. So this is how, given any expression, we can show it as a combination of inverter, OR gates and AND gates. So there might be some you might have seen some examples where you have been given some expression and asked to produce the output using gates. So you can see that the first thing we want to do in this case is x sum y, or x or y. So we need OR gate, and we give xy, and then we produce x plus y. Then we need to have product of this with x complement. So we need inverter to generate x complement, and then both of this we need to give to AND gate to generate the final expression. Okay, now how about second expression b? So we have x that we need to give to inverter, and we will get x complement. Now second thing we need to do is x OR z complement. So we will give x and z to inverter to get complement of z. Then both of these are given to OR gate to generate this sum x sum z complement. And then since we have complement of this, it is again passed through inverter, and then these both are given to AND gate to generate the final product. Now final equation C, how we can generate it using logic gates. So the first part has three variables x, y, z. So we are going to enter this to OR gate, because you can see that this is summation which is equivalent to OR. So we are giving it to OR gate, and then we are getting x sum y sum z. Then for the second part we have x, y, z but complement of each. So we are passing it through the inverter, each value x, y, z, and then we are getting respectively x complement, y complement, z complement. And since it is a product of these three are given to AND gate, and then we finally get the product. And then there is a product of these two terms here. So again we have to use an AND gate to get first term and second term, and that will generate the final expression which is shown by C. Again, it is very interesting to search and to find how you want to construct the circuits using this Boolean algebra. That is very interesting, and we had a whole course dedicated to logic gates, which was digital logic gates. I'm not sure if we do have something similar, but that was a very interesting topic. Now something we want to know that whenever we have logic circuits that can be used to add two positive integers, then we need to build such circuit, and those are called as adders. So first step might be a half adder which adds 2 bits but which does not carry. So whenever we are adding to any two numbers, what we did is whenever there is a carryover, we have to store that carryover again. So in half adder we do not accept carryover, only the summation part we are accepting. And then here we can see that if we have, so how the half adder should work. So if we have 1 1, then the sum is 0 and carryover is 1. So if you have 1 1, if you have the addition, bitwise addition you are doing or summation you are doing, then you get 0, you have carryover 1, and then you get 1. So you get 1 0. So if you see logically also, 0 1 and 0 1 should give you 2, and 1 0 is 2 in digital logic. So here we can see that the summation is 0 and carryover is 1. If you add 1 and 0, then you get summation as 1 and carryover as 0. If you add 0 and 1, then you get summation as 1 and carryover is 0. And if you add 0 with 0, you get both 0. So here how we can generate that is shown by building it with logic gates. So if you want to build, so what will give me such output? So you can see that the carryover output is exactly same as AND gate. So when both x and y are 1, I should get 1. So they are using AND gate to generate the carryover. But how about the first part? And the first part xy, we can get it by adding it. So if we add x and y, we should get, so 1 and 0 you get 1, 0 and 1 you get 1. But we cannot use OR gate here because if we just use OR gate, then this bit should not be 0. So we need to do something. So we need to use OR gate, and then we have to AND both of this, so that the summation will be x or y and x y negation. So whenever the carryover is not 1 at that time, only the summation is going to be 1. So here whenever the carryover is 1, the summation is going to be 0, and so on, because we are taking complement of that and we are adding it just to manipulate this, because directly it cannot give us the correct summation. The OR gate will give us 1110 and we want here 0. So we are taking complement of xy. So whenever the carryover is 1, the summation of 1 is going to be 0, but all the other cases the summation is 1. And this is a logical implementation or implementation using logic circuit. Just to give you an idea how these logic circuits work in computer science, that we can really build different operations or bit operations we can do using this logic kits, and then full adder which will take care of all the carryovers and things like that. So this is again this is one example of full adder, and it is used to compute the sum bit and a carry bit when 2 bits and carry are added, and then we can do that using 2 half adders. We can build this. So this was just one application of the logic gates, how we can make addition of bitwise examples or expression. So I think this so this chapter actually ends here, and this was the last slide. So these things I wanted to cover as part of this course, and next time where I will go over to some concepts of chapter 13, but again, as I said, those will not be part of your final exam, but we are going to cover that as part of discussion board assignment. So we'll stop here, and then I will talk to you in the next class.